Hello, my name is Amir, and I'm presenting a quick overview of our research paper for International Conference on Learning Representations 2026. You ever look at a game or a movie like Avatar and wonder how it looks so real? All those tiny details like textures and realistic skin? Well, behind that realism is a complex process, and it has been a big challenge for 3D artists. This process is called UV mapping that converts a 3D mesh into a 2D layout. For simple shapes like a sphere, this is straightforward. But for complex objects like a dragon, it becomes harder and time-consuming. In this work, we want to see if we can automate the UV mapping process using AI. To tackle this, researchers have proposed many UV mapping methods that focus on geometric properties. Specifically, each triangle on the 3D mesh is mapped to a triangle in 2D while keeping distortion as low as possible. Even though these properties are important, they are not enough for many real content creation tasks. In this work, we focus on two perceptual properties. First is semantic awareness. This means the UV charts should line up with meaningful parts of the shape. Second, visibility awareness, which means cutting seams should be placed where an observer is less likely to notice them. To handle this, we introduce an unsupervised framework that adds these two objectives on top of geometry-preserving objectives. For semantic awareness, the process has three steps. First, it partitions the mesh into semantic parts. Then it runs an unsupervised MLP backbone on each of those segmented parts to generate UV charts. And finally, it gathers up all those UV islands and packs them into a final UV atlas. But the question is, how does it automatically partition the mesh? This is where shape diameter function comes into play. Intuitively, shape diameter function maps each surface sample to a scalar that estimates the local object thickness. Areas with a similar thickness, like the handle of a mug, get grouped together. So now that we have artist-friendly UV islands, what about the seams between them? To do this, we use ambient occlusion and we treat it as a visibility map. In other words, areas that are naturally darker, like under human arms, are less visible. So they are perfect places to hide seams. Our visibility-aware pipeline has four main steps. First, we compute ambient occlusion for each vertex on the mesh. In the figure, yellow shows exposed regions and purple shows hidden regions. Second, we use a bidirectional cycle mapping MLP to generate a candidate UV map. Next, we extract cutting seams directly from the learned UV map. For each vertex, we look at its neighbors in 3D space and compare how far apart they end up in the UV space. If two points are close in the 3D space, but far apart in the UV space, that means a cut happened between them. So we mark those as seam points. Finally, we use the ambient occlusion values we computed earlier to define a loss that pushes these seam points toward more hidden regions. We combine this with the standard geometric losses and train everything together. We compare our semantic-aware UV mapping with state-of-the-art methods. Our method produces UV charts that align much better with meaningful parts of the shape compared to the baselines. Here we also compare visibility-aware seam placement. The top row shows the ambient occlusion, and below that are the seam visualizations. Our method places more seams in less exposed regions, which makes them less noticeable in the final result. We also validate this using a checkerboard texture comparison. Because our method pushes seams into less visible areas, the checkerboard looks much more continuous. In contrast, the baselines show clear seam artifacts in the zoomed-in views. We also compare our method quantitatively with existing approaches. First, we ran a user study with 115 participants, including both general users and experts like UV and modeling artists. The results show a clear preference for our method over the baselines. Second, we report automatic metrics for semantic awareness, visibility awareness, and geometry preservation. Our method consistently performs better in terms of semantic and visibility quality. One important takeaway is that this improvement comes with a small trade-off. We sacrifice a bit of geometric accuracy, meaning slightly more distortion, but this is expected when optimizing multiple goals at once. In practice, semantic alignment and less visible seams are often more valuable, especially for tasks like editing and asset reuse. And the nice part is this trade-off is controllable in our pipeline, where you can adjust the weights in loss function to balance between distortion and these perceptual qualities. Thank you for your time and attention.